calculating the pH of a salt solution. So to do this, don't freak out that it's a salt solution. All you have to do is look at the salt. Your salt is going to be, well, it could be a neutral salt, right? It could be like, I don't know, sodium chloride, and those are both neutral ions, in which case the pH is going to be 7. Or you could have an anion that is basic, in which case you're just going to base your calculation on a reaction of that basic anion with water. Or you're going to have a cation that is acidic, and you're going to base your calculation on the reaction of that acidic cation with water. Okay, so you got to look at your salt. Okay, so a salt is going to completely dissociate, providing it's soluble. We're not even going to worry about that. We're just going to assume. So here is our salt. What is that going to break apart into? Well, sodium is going to be the cation, right? So Na plus. And what all else is left over? Well, I'll put an AQ so we can see what's going on there. It'll be C5H5CO2 minus C6H5CO2 minus. So is that a weak base? I don't know. Is there any information in the question that could help us? Well, we are told something pretty significant. We are told that benzoic acid is a weak acid. Is there a relationship between this anion that we have written and benzoic acid? Well, I can see there's a difference of a proton between them. There is a proton between us. So this is our acid, and when it donates a proton, it forms its conjugate base. So what we're dealing with here is a basic anion. It's a basic salt, right? Because this C6H5CO2 minus anion, I'm going to go ahead out on a limb and call it the benzoate anion, is the conjugate base of benzoic acid. So this conjugate base itself is going to react with water. It's going to act as a base. So what do bases do with water? Well, any weak base is going to react with water, and a base is a proton acceptor, so we're going to accept a proton. So just stick a proton to it, and we're going to liberate hydroxide. So we know in order to get the pH of this solution, we are going to be solving for the concentration of hydroxide. Okay, so what about our specific situation then? So again, just go with it. We're going to take this base, this benzoate anion C6H5CO2 minus AQ, and we are going to give it a proton. If I give it a proton, I'm going to stick an H on the front. That's the hydrogen part of it, C6H5CO2 minus. Now we already had a -1 charge, so if I add +1 to -1, it's going to end up being neutral, and that is benzoic acid, okay? And we are also going to be liberating hydroxide ion, okay? Whatever happens after that, we don't care, right? This is as far as we are going with this. So that is the equilibrium we're looking at. So can we write an equilibrium constant expression, a base protonation expression? We can. We need Kb though, right? So don't worry, we're going to get there. So we can write a base protonation constant expression, but the problem is we only have the pKa of benzoic acid, but that's okay. First of all, P's don't worry us. P just means minus log, right? So if we've got our pKa, then our Ka for our benzoic acid, HC6H5CO2, is going to be minus log, 10 to the power of minus pKa. Which is going to be 10 to the power of whatever it was, 10 to the power of minus 4.20. So that's going to give us a number for Ka. We can work with this, people. That is going to be Ka blah, 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 6.310 times 10 to the power of minus 5. Okay, so already looking at the relative magnitude of that, our conjugate base, our benzoate anion, is going to be pretty weak in comparison. Okay, so how am I going to get Kb for the base? Well, we know there's a relationship between Ka and Kb, right? Kw, the ionic product for water, is Ka, the acid, times Kb for its conjugate base, and that's going to be exactly 1 times 10 to the power of minus 14. So now we can solve for Kb for our benzoate anion C6H5CO2 minus. that is going to just be Kw over Ka. So Kw over Ka for our benzoic acid, which we just worked out. So 1 times 10 to the power of minus 14. Might have to be careful how you stick this in your calculator. Divided by Ka for my benzoic acid, which we just worked out as 6.310 times 10 to the power of minus 5. Cha-ching! What are you equal? Ha ha ha. 1.601 times 10 to the power of minus 10. That looks like the right order of magnitude to me. That makes me happy. So now we can finally write our Kb expression, right? So Kb is the concentration of our benzoic acid, C6H5CO2, times the concentration of hydroxide over the concentration of our benzoate ion, C6H5CO2 minus, and that is going to be equal to the value for Kb, what we just calculated, of 1.601. Sorry, I had a bit of a sneeze there. 1.601 times 10 to the power of minus 10. Okay, so now we're rolling because now we just have a nice table. We can do these in our sleep. It's going to be fine. What have we got? We got our benzoate anion C6H5CO2 minus. I wish I had the foresight to control C that, but here we are. So HC6H5CO2 for our benzoic acid product, and then hydroxide for the hydroxide being generated. So initial change, equilibrium concentrations, here we go. So the initial concentration is going to come straight out of the concentration of our salt solution because look, that goes 100% to the right, okay? So for every 1 mole of sodium benzoate that dissolves, we get 1 mole of sodium and 1 mole of the benzoate anion. So that's just going to be a concentration of 0.42 straight from the question. Okay, we have 0 of our conjugate acid to begin with and 0 of hydroxide at the beginning. So the change, this reaction is going to proceed towards the right to reach equilibrium. Therefore, the change in our benzoate anion will be minus X as it's getting used up, and our benzoic acid is getting formed and our hydroxide is getting formed. Add down the column to get our equilibrium concentrations in terms of X. This is becoming a very familiar thing now, okay? So we can substitute those into our Kb expression and solve for X, can't we? So Kb is going to be X times X over 0.42 minus X. And that will be equal to the value of Kb that we calculated, which was 1.601 times 10 to the power of minus 10. Lovely jobs. We're going to do the X is small approximation, okay? So if X is small, that is going to end up with it being X squared over 0.42 equals 1.601 times 10 to the power of minus 10. Therefore, X is going to be the square root of 0.42 times 1.601 times 10 to the power of minus 10. Make it pretty. Try and draw a kind of square root thing-ish. Okay, and so X, which remember is going to give us the equilibrium concentration of hydroxide, is I don't know, 8.2 times 10 to the power of minus 6. So we do have to do a quick checky check to make sure the X is small approximation is valid. Now, I've very quickly eyeballed this already because I looked at the 0.42 minus X. If X is something times 10 to the power of minus 6, that is like 6 orders of magnitude difference, right? So it's not going to make any difference to the 0.42 minus X. You can calculate the percent ionization, right? So 8.2 times 10 to the minus 6 divided by the initial concentration of our weak base of 0.42 times 100 is going to give us 0.002% ionization. So X is small is good. So we can say it's valid. That's fine. Okay, so then the last thing we have to do is calculate our pH. So 2 ways to do that. I will show you both because I don't know what you've been taught or what makes more sense to you. So one version is using Kw equals the concentration of hydronium times the concentration of hydroxide. Therefore, we can use that to calculate the concentration of hydronium from hydroxide, because Kw is always 1 times 10 to the power of minus 14. I feel like I might have said that about 15 times already in this little video, but you know, it's kind of crucial to the video. Therefore, the concentration of hydronium in this case will be 1 times 10 to the power of minus 14 divided by concentration of hydroxide we got was 8.2 times 10 to the power of minus 6. That comes out to be 1.22 times 10 to the power of minus 9. Now we can do the whole minus log thing to get our pH, can't we now? So pH is minus log of the concentration of hydronium. So that will be minus log of whatever we just calculated, minus log of 1.22 times 10 to the power of minus 9 equals a pH of 8.9. Okay, so that's method 1. If you prefer, you can use the POH method 2, but you just got to be careful, because the first thing you're going to do is calculate the POH, which is minus log of the concentration of hydroxide you just calculated. So that shakes out to be 5.1, right? Minus log of the 8.2. So this is very deceptive because it looks like a pH, but it ain't. Okay, that comes out to be 5.1. Dead giveaway is that if it was a pH, that would be acidic, and we know we're dealing with a weak base, aren't we? So I'll scooch this over a little bit, make it fit, make it fit. So then we have to use pKw, which is pH plus POH equals 14. So we just have to subtract that number, right? So pH is going to be 14 minus 5.1, which is going to give me that 8.9. Okay, so either method is fine, okay, but just caution if you use it. I like using method 2 just because the math is easier and I feel less likely to stuff things up on my calculator with writing times 10 to the power of whatever a few times and dividing and brackets and blah blah blah. But whichever method feels safe to you is fine by me. As long as you understand what you're doing, it's all good.